let us discuss one of the important definition here. Linear differential equations of second and higher order. So here, a linear differential equation of order n is a equation of a form. So here, a linear differential equation of order n is a equation of a form an of x into d power ny by d into x power n plus an minus 1 of x into d power n minus 1 y by dx power n minus 1 plus so on up to plus a1 of x dy by dx plus a naught of x into y, which is equals to q of x. This we are considering as equation 1. So this is the form of an equation of order n. So this form of equation we are considering as equation 1. Now here where a naught comma a1 comma so on up to an and q of x are continuous real functions. So these are the continuous real function, or these may be constant. So if q of x equals to 0, then equation 1 is called homogeneous linear differential equation. Listen here, if q of x which is equals to 0, then equation 1 is called as homogeneous linear differential equation. Next, if q of x not equals to 0, in the case if q of x not equals to 0, then it is called as a non-homogeneous differential equation. If equals to 0 means homogeneous linear differential equations. Not equals to 0 means q of x not equals to 0 means non-homogeneous differential equation. Now let us discuss the operator form of this definition. So what we are doing here, we are substituting d by dx equals to d. So the place of d by dx, what we are substituting here? Capital D in equation 1. Then we get an of x into d power n plus a minus 1 into d power n minus 1 plus so on up to plus a1 of x into d plus a naught of x. Here we are taking y as common for whole, which is equals to q of x. Now here what is the general solution? So general solution of equation 1 is y equals to yc plus yp. Where, so what is here yc? Complementary function. Yc means it is a complementary function. Yp is a particular integral. Yc is complementary function. Yp is called as particular integral. Let us discuss solution of homogeneous linear differential equation with constant coefficient. So here an into d power n plus an minus 1 into d power n minus 1 plus so on up to plus a1 into d plus a naught. What we are taking here, y as common, which is equals to 0. So what we have discussed earlier, q of x equals to 0 means it is a homogeneous linear differential equation. So in the place of q of x, what we are substituting here? In place of q of x, 0. Earlier discussed, if q of x equals to 0, then it is called as homogeneous linear differential equation. So we are taking here, in the place of q of x equals to 0. So this we are considering as equation 2. Now, general solution of equation 2 is y equals to yc. Yc here, complementary function. Now let us discuss method to find complementary function. Now let us discuss this method stepwise. Step 1. So write the given equation in operator form. First what we have to do? We have to write the given equation in the operator form. That is f of d equals to 0. Next, in step 2, what we are doing here? Write the auxiliary or characteristic equation by substituting d equals to f. So this equation is known as the auxiliary equation. So what is the auxiliary equation here? Auxiliary equation AE equals to an into m power n plus an minus 1 into m power n minus 1 plus so on up to plus a1 into m plus a naught, which is equals to 0. So this is the auxiliary equation. In the place of d, what we are substituting here? M. First we are writing the given equation in the operator form, that is f of d equals to 0. And next, in step 2, we are writing the auxiliary equation by substituting d equals to m. Now in step 3, find the roots of auxiliary equation. So in step 3, we have to find the roots of this equation, of this auxiliary equation. Now, next in step 4, then the following 3 cases may occur. So here 3 cases are occurring. What are those 3 cases? First one, the roots are real and distinct. So the roots are here, roots are real and distinct. Next, roots are real and equal. Here 3 cases. What are those 3 cases? Roots are real and distinct, roots are real and equal. Next, roots are imaginary or complex. Next in step 5, then the complementary function for real and distinct roots. So here, if m1, m2, so on up to mn are n distinct roots, then the complementary function. What is the complementary function? If these roots are real and distinct, means the complementary function is yc equals to c1 into e power m1x plus c2 into e power m2x plus so on plus cn into e power m into n power x. Next, if roots are real and equal. So if roots are real and equal, that is m1 equals to m2, so on equals to m. Then what is the complementary function here? yc equals to c1 plus c2x plus c3x square plus so on up to cn into x power n minus 1 into e power mx. Next, in the third case, if roots are complex, that is complex means m equals to a plus or minus I into b. Then what is the complementary function here? yc equals to e power ax into c1 into cos bx plus c2 into sin bx. So these are the complementary functions of the 3 cases.